Okay, so Unit 10 is our final unit, and we got into Introduction to Standards and Non-Destructive Testing of Industrial Materials. So, when we test the materials all the time, and you have to test it, and the purpose of testing them is because we want to understand the properties of the materials. And if you understand the properties, we can make many products out of it. So the materials are tested for safety and product performance, their quality, the product quality. We test them for new product and process development, and we test them for scientific research. Okay, standards. So if you think about the United States, we have ASTM, so that's the American Society for Testing Materials, and every time you test the materials, we have to follow something called standards. Okay, so this ASTM was founded in 1898, and it is a scientific and technical organization. And what it does is it produces voluntary standards. In fact, it is one of the largest sources for voluntary standards. So there are 6 principal types of standards this organization is producing. So they are standard test method, standard for specification, practice, terminology guide, and classification. Okay. By following the standard, we're getting rid of all the steps that are taking time. Like you don't have to worry about what size is shape. You don't have to worry about what kind of properties. You don't have to worry about any of this. Okay, all you have to do is just follow the standard and the dimensions that they specify for you. So it's kind of like saving time for doing that. And that's the only reason why we pay a lot of money to these organizations. Okay, it's kind of like a buyout, buying time, right? For convenience. Okay, so the second organization is ANSI, that's American National Standards Institute. It was founded in 1981, and it coordinates the standard activities. And this organization performs on the national level. So their goals are, well, they identify needs for standard, they protect public interest, consumer rights, and they promote standard development. They also do implementation, and they approve American national standards and represent interests of the United States in non-governmental international standard works. Okay, so it's a pretty big organization. And the next organization is there are many of them, so I listed here. The very first one is AISI, American Iron and Steel Institute, Society of Automotive Engineers, SAE. This one is pretty big. American Concrete Institute, ACI, Society of Plastics Industry, SPI, National Institute of Standards and Technology, NIST. This one is also pretty big. Department of Defense, DoD, Food and Drug Administration, FDA. So both of them are very big as well. So these agencies, what they do, they make standards, alright, related to materials for the industry. Okay, so let's take a look at each agency. So the very first one is American Iron Steel Institute. We call it AISI. So this organization is a trade association when they begin, and it governs the material specification standards. And what they concentrate is in iron and steel. So what they do, they provide high quality value-added products to a wide array of customers. They lead the world in innovation and technology. In the steel production, they produce steel in a safe and environmentally friendly manner, and they increase the market for North American steel in both traditional and innovative applications. So these are pretty standard thing in organization, okay? DOS in USCITS and many other organizations relatively similar goals. And the next one is SAE, our Society of Automotive Engineers. So this organization promotes structural material applications in industry like automotive and aerospace. It establishes the standards related to structural steels and steel alloys, because we're making cars, making rockets, spaceship, things like that. Okay. The next one is our Concrete Institute, so that's American Concrete Institute, ACI. What it does, it recommends standards regarding your cement, materials made from cement, and applications, alright, made from cement. So it's all about cement. It's also dedicated to improving the design, construction, manufacturing, maintenance of concrete structures and facilities. So that's very, very big because we have cities, towns, alright, and small towns all over the United States, and they have structures. Structures mean like buildings, okay? And facilities are like our school, like there are many buildings on campus. Government, alright, buildings, private and public buildings, everything, okay? So it develops and disseminates information and standards. They concentrate only one material, and that's concrete, okay? Everything about concrete. Next one, plastics. So the Society of Plastic Industry, in the other name is Plastics Industry Association. It's the same thing. It is a trade association, and they deal with plastics or polymetric materials. It promotes proper uses of plastics by establishing the standard test procedures, specification for plastic pipe, bottles, furniture, packaging, and various resin. So that's what they do. Okay. Alright, the next thing, your NIST, and that's the National Institute of Standards and Technology. So we belong to this world. Okay, so it was actually, in the beginning, it was known as NBS, so National Bureau of Standards. This agency goals are strengthening and advancing the nation's science and technology, very broad, and facilitate their effective application for public benefit, broad goals. It also conducts research and provides the basis for the nation's physical measurement system, and offers scientific and technological services for industry and government. It promotes competitiveness for industry, maintains the equity in trade, technical services, and promote public safety. So when you think about NIST, first thing is research, okay? And second thing is going to be the standard. Okay, there it is. The word is in the name of this agency, and they definitely concentrate on science and technology. Okay. Department of Defense is DoD. So it's a government agency, and they do like military applications for materials. And within the DoD, there are many agencies, okay, and they do their own functions. It's a very complex organization. So the sub-organization and DoD is a parent organization. And all of them are charged with maintaining various military standards. So they concentrate on military standards, right? So what are they doing? Standards for material, processes, products. And every time you have to deal with standard, what we're trying to do is maintain, okay, and improve the quality, performance, military equipment, and supply. We have lots of military equipment, from guns all the way to airplanes, alright, your convoys, your military trucks, and then your armaments, including various technologies, okay, and all these technologies are made with different materials, industrial materials, because we're making so many different equipments. So anyway, they control all of that, and their concentration is the military. Food and Drug Administration is definitely in the name, yeah, for public. So what they're doing is they protect the health of the nation, so all Americans. So they try to protect the food, the drugs, the cosmetics, because they are made of, okay, chemicals. They are made of, I would say, like biochemicals and chemicals all together, yeah. And all of them are in direct contact with the human body. We eat this, we use this, right, to protect ourselves from germs and microorganisms, and we use this, right, on our skin. So therefore, everything to do with human system. So therefore, this is a very important organization. So implications for material scientists and engineers are definitely related to processing the equipment, containers, medical devices, and implants. So every time you want to produce something, you definitely need to submit, okay, your product to FDA. So FDA is, we see it as a big quality control group, yeah. So if you're in my line in quality assurance or quality control or quality systems, then you can definitely apply at FDA, okay? And they have lots and lots of equipment, okay, and devices. Alright, so now let's get into testing. Non-destructive means when we do the testing on the material, you're not going to get any kind of damage or failure of the specimen. And we call that specimen is just a test material or test piece. We call that non-destructive test. It's a really fast test. You don't really need any kind of extensive preparation for the test piece or specimen. And we use it in production control. We use it on construction site for inspection. So what we do here with these non-destructive tests is we try to find the flaws in raw material or semi-finished products before you do any machining or fabrication on it. So this belongs to the quality system, quality control, and all these tests that we do is for production cost saving. So cost analysis is a huge part of quality control, and we always have to analyze the data and come up with all kinds of analysis on cost, okay, expenses. So here we have a list of tests that we do for non-destructive testing, commonly used one. So we have Penetrant Test, Radiographic, Magnetic Particle Test, Ultrasonic, we have Eddy, and we have Acoustic Emission and Infrared Thermography. Okay. So let's get into the very first test, is Penetrant Test. Somebody mentioned something about the lab activities. So we do have, when we go full in-person class, we do this testing for the industrial material class. So Penetrant Test is a simple method, and it detects the defects, right? The flaws with the surface opening. Surface opening is nothing but just an opening on the surface. So what we do, we clean the surface and then we dry it, and then we spray, okay, the penetrating dye fluid like that. If you don't have a spray, you can swap onto that surface, and then you're going to allow that part to stand for sufficient time. So the penetrant is going to fill any surface cracks, right? And all the excess penetrant is going to flush out from the surface when you use a warm water or cleaner on it. Then we carefully dry the surface and coat with another agent, okay, called developer. This is just a solvent. So the dye left in the surface, or the surface crack, is drawn to this developer that we apply, okay, later, and it shows the crack on the surface. So after some time, and we call that developing time, meaning like we're giving some time for these reactants to mix together, okay, the parts can be inspected. And what you're doing is you're looking for the defects exposed on that surface, okay? So if you want to wrap that up, penetrant test, we're going to use the penetrant. We're going to detect a surface with a crack, so spray on it, okay? And then you wait to allow that penetrant to fill in any of the cracks on that surface. Then we're going to use the water and cleaner. Then we're going to let it dry. Coat it with a developer, okay, and then wait. And that developer is going to react, yeah? React with the dye left on that surface. So later on, you can be able to inspect on that surface by looking at or looking for the defects exposed on that surface, okay? So that's what we're trying to do. So when you take a look at it, this is what you usually see. See that crack? And these are just a dye mixed with your developer. So when visible dyes here, red dyes are used, the parts are inspected under normal white light. So you can see this little white light right there. An operator is going to be you. It's going to look for the red dye. Again, it's a white black background. So you have a white background, and we are looking for the red dye. Okay. And if we use the fluorescent dyes, you can see the parts, alright, under a black light, not a white light. Red dye, white background, fluorescent dyes is going to be a black light, black background, okay? So try to remember two different dyes. And for fluorescent dye, you or operator is going to look for a bright yellow-green color against a deep blue-violet background, okay? So in both cases, operators are looking for small amounts of penetrating dye that show your crack or your flaw or your defects, Okay? So it's kind of like filling the dye in the crack and then shine a light upon it to be able to differentiate that crack. So it's pretty easy to do this type of test. Okay, this one is from the textbook diagram. It's a two-dimensional diagram where you can see the crack and you can see the penetrant, okay, filling into that crack. We also call the crack flaw or defect. This is your part. So the penetrant test, we're going to start by coating the clean surface with penetrant, and that penetrant is going to seep into any crack on that surface. Then when you take a look at B, excess penetrant, we will remove it by cleaning the surface. And then you're going to apply the developer. So see, developer, these little dots right there, star dots right there. So surface cracks are indicated by a small amount of penetrant. That penetrant is going to react with the developer. So see this, where it was originally, it's going to come up, yeah, drawn out by the developer. Okay, the next test is radiographic test. It's like your dental x-ray inspection when you go to see your dentist. Especially for the first time, they will definitely x-ray you, all your teeth, right? So it uses short wavelengths such as x-ray, beta rays, and gamma rays. So this test using x-ray, so what this ray can do, it can penetrate a material. Of course, not going through the whole thing, but up to a certain level. It also depends on the internal structure of that material. And then we're going to place a file behind the part and expose the radiation source, penetrating that material. So after some time later, you're going to see a film is developed and then shows an image. Okay, in this instrument, you can see the image of your internal structure of the material. So if you go back to your dentist, then they take your x-ray and then the nurse is going to go out and then she will come back in and give you your x-ray. Yeah? And you can see all your teeth. So that's what we're saying here. You get a film developed and then show an image of the internal structure of that material. And this test method is useful for we detect the flaw in welded joints, especially for critical structures, okay, in your products. So sometimes the welded joints we can see inside. So at that time we gotta use a radiographic test to see inside. Okay. Again, we use X-ray, beta, and gamma rays because they can penetrate. Okay. In operation, safety precaution you have to take because we don't want any kind of accident with this radiographic test. Radiographic assistants, they have to wear safety shielding like this guy. They must also carry an individual direct reading pocket, something called dosimeter, and either a film badge or thermoluminescent dosimeter. Overexposure to X-ray, they are not very good. Overexposure to beta, gamma ray, any kind of I should say like very strong rays, it can lead to injuries or health problems like cancer, yeah, because they can penetrate material. So if the rays penetrate into you, it's no good, you know. So make sure you avoid exposure, long exposures. This is a textbook diagram, and here you can see the radiographic method. And here, see that this little line right there? And that's the film. And you're going to place that behind the part. So here, you can see this little white, and that is your part. We place the film behind the part. and it is exposed to X-rays. So any discontinuity in the part, so you can see here, see the discontinuity right there. It's going to appear on the film, yeah, due to differences in the X-ray absorption. So this is continuous, and that is continuous, and here you can see the flow. See that? So here we develop the radiograph, and we can see, voila, see? The part right here has a defect. So just showing where the floor is. The next test is a magnetic particle test, and we can use it for ferrous alloys. So you're going to begin with laying the steel component across the arms of the magnetic machine. Since this is a magnetic particle test, we're going to use a magnetizing machine. So a special magnetic power is sprinkled on the magnetized part surface. Okay, so you're gonna just sprinkle some magnetic powder on that part. So what we get is a flux. So lines of magnetic flux are gonna intensify across the crack. So that's magnetic powder is drawn to the crack, making it visible. So we're using the magnetic attraction in this particle test. Particle being the powder we're using, the powder we're sprinkling on the magnetized part surface to find any kind of crack in that surface. So magnetic particle test is used for wet and dry magnetic particles, and we can inspect the surface. In automobile, right, we use this test because we want our cars or body to be very, very flawless. So wet particles, we use them for detection for hairline surface cracks. So basically, just remember we use the wet particle magnetic test for surface cracks. Because these particles, they're typically used in stationary machines. Stationary machines are machines that are standing in a fixed location, where they can be continuously, we agitate that particle, pump the particle, recycle the particle through a spray nozzle, yeah? And dry particles are designated for use with portable equipment. So if you have like portable equipment, you're going to use the dry particles. If you have like a fixed machine, you're going to use the wet particles. So dry particles, portable equipment, they are effective on large parts, and what we're inspecting, rough surfaces, yeah? So when you think about the particle, we can only use one time, and we can recover them, so therefore particles are just one-time use. This is a textbook diagram, and you can see a flaw right here in the component. So this S and N is just an indication of your magnetic flux. Alright, we're not drawing the lines all around here, but you know that every time we mention S and N, meaning you are dealing with the magnetized part, okay, with all your flux all around the environment. And we have elongated magnetic particles. So here you can see this little four, right, elongated little lines right there around the crack or the floor in the part is your particle. Yeah. Ultrasonic test is another one. This test uses sonar or sound. Sonar means sound wave system, and we use that sound wave to detect the floors. So ultrasonic waves, we're going to produce it by using the piezoelectric effect, and we definitely use a quartz crystal transducer, right, to get this effect. So the wave is going to come out And these waves are outside the audible range, right? They are sound waves, so therefore normally between 20 kilohertz all the way to 50 megahertz, right? That's just a frequency unit. So review your physics. The sound wave, they travel inside the material, alright? So these waves can be reflected by any boundary, like outer surface or internal floor. So when they bump into an internal floor, they're gonna bounce back, alright? They're gonna reflect. So the transducer, the one that we use, the quartz crystal transducer, is going to send a wave into the material being tested. If you are new to the transducer, it's a kind of like a very small, alright, a little cylindrical kind of like thing that we use. Okay, it's just electric or electrical device, and what it does is basically convert the energy from one form to another. So energy we already knew is just ability, right, of these objects to do something. So this transducer can convert the ability of certain objects, right, into different abilities. Okay. Or you can say I can convert the energy from one form to another. If I use it so formally, then you lose touch with the real life. So energy meaning ability, okay, just something that something can be able to do. Alright, so the time the sound wave travels in the material depends on the characteristics and thickness of that material. So when we think about the sound, you have to know that this is just a little thing, alright, and it needs a media to go, okay, to go from one location to another. So for the sound wave to go from here to another, alright, you definitely need the media, like the domino. Otherwise, it can't go. Right? If you're in a vacuum, sound wave cannot be able to go through that vacuum. It's just gonna stop where the media ends. Right? It's very important for the sound wave to have some sort of medium to travel on it. Okay. So again, it depends on the material, character, and thickness. So if there is no defect in the material, your sound wave is reflected by the other side of the material. And you're going to have the total travel time corresponds to the thickness of that material. So you can see that you have material, and then you're testing by sending the sound wave through it, and it's going to come out, and you will be seeing a pulse, right? 1 and then 2. But when the sound wave is going to hit, if you have like a floor here or something like that, okay, it's a different story. So if you have a floor, what it does is going to stop right there. So what happens is you're going to see in your device, stop, okay? So you can see there is a difference in the time. So here, from here to here is the total time. Right now, your total time is from here to here. So therefore, there is a difference of this amount, okay? And that is a reduction of time. So however the sound wave hits the floor inside the material, the travel time is reduced accordingly. Where it hits is going to stop, yeah? Because sound cannot travel in a vacuum. It needs a material to travel, and this is a proof of it. Okay, so you'll review your physics. So the reflected wave is shown closer to the transmitted beam or initial pulse. So therefore a floor is indicated. You can see it in the screen. Yeah? Here this guy trying to see the inside of the cylindrical tube. Right there to maintain this system, big system he's maintaining. So it can be used to detect flaws in all types of material, including the composite. So let me erase this. Textbook picture. And we're going to start from this diagram. So this is showing you the ultrasonic testing through a 2-dimension. And we're going to detect the internal flaw. Okay. And now we're going to draw a pulse, because we're sending the sound wave through the material. And your flaw is right here. So the ultrasonic pulse takes a measurable amount of time to travel through a part without flaws. Okay. So this is without flaws, and it's going to go initial reflected. And this one, when the ultrasonic pulse hits a defect inside the material, right, the travel time for the pulse, see, is reduced. So either you can, the detection can stop right there. Okay, so that's where you're seeing the gap, which is the difference right here. Okay. Okay, so now here is the textbook picture. This is a close-up, and here you can see the waves. Okay, and that's exactly where the internal material, right? How the sound travels inside of any of the material that you're testing. Okay. We can also do it on composites. These are composites are just mix. Mixing 2 or 3 different things, 2 or 3 materials all together. Eddy current test is a very common one that we use in industrial engineering, electrical and mechanical engineering, alright? Also, of course, in technology as well. So it involves the use of, we use alternating magnetic fields. So these tests, we can use them on any conducting material. Okay, your material got to have a conductivity, otherwise it won't run. So let's refresh eddy current. So when an alternating current is used to excite a coil, don't forget what current is, the flow of your electron. Okay, and that flow is going to excite a coil, meaning like inside of the coil material, which is conductible, right? Your current is flowing in it. So what we got is an alternating magnetic field. So the magnetic lines, every time you have a magnetic field, we've got lines and flux. And they're going to be concentrated at the center of that coil. So as the coil is brought near an electrically conductive material, the alternating magnetic field is going to penetrate the material and generates continuous and circular eddy currents, right? So that's what it does. So here we can take a look at with the picture. So larger eddy currents are produced near the test surface, and weaker eddy currents are produced inside the material. So here, again, your magnetic flux impulse, right? And here we have our voltage. And that's how your currents are flowing in that direction. Weaker eddy currents, so what it is saying is that you can see it inside of the part, okay? The larger ones is going to be on the surface. So eddy currents include the additional magnetic fields, and that's going to interact with the original magnetic field. Meaning like you can use another magnetic field on top of the first magnetic field. Then you're going to observe. So any change in that current, you can detect it. So how do we detect the eddy current change? We detect it by change in the interaction between the first, right, and the second magnetic field. Now if you have a crack, so a crack in the test material is going to obstruct that current flow, okay? It's not going to be smooth like the part without the defect. So with the defect, your current is going to get obstructed. So therefore, it's going to lengthen the eddy current path. Okay? It takes longer time because of the obstruction. And then it's going to reduce the secondary magnetic field, meaning like reduce the strength of that magnetic field. Okay? So therefore, every time you observe the weakness in the second magnetic field, and then you observe the length is longer in the current path, you definitely know there is some sort of defect or fault. Yeah. Here your eddy currents, and this one is your material, this part. And here you can see the eddy currents magnetic field. And this is your coil, okay? And here on the surface, you can see the large eddy currents, and inside you're going to see the smaller ones. And you're going to observe that current, okay? Path. If it is taking longer, there is some sort of flaw or defect in that path. And you're not doing only this surface, you're doing the whole, right? So the change in the secondary magnetic field, we're going to sense it by using that coil and then indicate it by the appropriate instrument like that. Yeah. So this guy is testing. So if a test coil is moved, you're going to move it, or crack a defect in a metal part at a constant clearance and constant speed. The momentary change, you're going to see the change, okay? It's going to happen in that coil reactant and also coil current. So an eddy current instrument can be used to detect cracks, seams, lets, pits, inclusion, and other defects. So your current, it's on the surface, but you can't read it directly. So therefore, we have to use this coil in order to transfer that, alright, the seam or the pattern of the flow. So that's how we connect, alright, to the instrument. Otherwise, whatever that's happening on the surface or inside, you cannot be translated to the machine. So in order for you to translate it to the machine for the same pattern, you definitely use the coil, okay, the conducting coil. So it can also be used to measure thickness, electric conductivity, magnetic permeability, hardness, or physical dimensions, because these properties are all related to the eddy currents on the surface, okay? So when you read this, you can understand it. All you have to understand is what's happening on the surface is transported to the machine through these coils, okay? That's all. Alright, this one is your textbook diagram. So in an eddy current test, you have your primary field of the test coil is going to enter the test part down there and then generates your eddy currents. And it's going to create the secondary, alright, field, which is going to just appear, right, because of that test coil generated the first field, that's going to generate the second field, yeah? So any flaw in the material is going to change the current, and you will be detecting through that instrument coil, yeah? So here is your part, and there is your little flaw, one of the cross section. So this can be anywhere, right, in this part. We're just showing two dimensional cross section here, and you can see the current going on top and also inside of that part. Okay. Alright, so the next test, this is also a non-destructive test, is acoustic emission. So this one is an elastic wave generated by the rapid production of energy or release of energy from a defect within that material. So when you look at this part, you can see a crack right there. Okay, and this crack is generating, right, elastic wave. Okay, so the wave is going to propagate through the solid to the surface of the part, and which is then detected by one or more sensors. Okay, so we have part, we have a crack, we have the wave being generated, and those waves are going to be captured by these sensors. Yeah. So the sensor is just a transducer again. Every time you think about transducer, there's a little thing that's going to convert the energy from one form to another. So here in this case, convert a mechanical wave, and we're going to send it to electrical signal. Yeah. So that signal is, we're going to analyze it to determine the location of that crack. And we also call the crack as a failure. That's just a word, right? The same thing, crack or failure or defect. So when ultrasonic testing actively probes a structure, an acoustic emission system is going to listen to the internal emissions from that crack or defect. So the acoustic emission testing is very sensitive to defect propagation, alright, created by the structure load, because waves they're pretty fast, yeah. It is therefore very effective testing. And here is the textbook diagram, just showing the principle of the acoustic emission process. And you can see the part, and here are the sensor on the part, and you can see the wave propagated from the crack. Okay. And here the sensors are connected to your electronics or your instrument, right? The instrument has a display, so you can look at it with your eyes. Last one is your infrared thermography. Thermography, again, in kinds of heat. Yeah, you can see like that. We did some sort of a graphic one with Excel. Not as good as this. We can see the heat on Excel, but you can see a little bit of the location, okay, of the temperature. So thermal or infrared energy is radiation, and that radiation is emitted by an object based on its temperature. Okay, temperature meaning the little things inside of the material start to move and move around. Okay, how much are they moving is the indication of your temperature. So the greater the object's temperature, the greater the radiation emitted. But for infrared energy, it's definitely not visible to the human eye. So we need an instrument to be able to look. Yeah. So to see the images of that energy, we have to use this infrared thermography camera. Yeah. You shoot it and you can see the image like that. So these cameras, they can capture the infrared spectrum. So here you can see the little one right there. So infrared thermography has many applications in a variety of industry, and it can be used in commercial, residential construction, because we want to detect the heat loss around the roof, windows, and doors. Other applications, we use to inspect the equipment, especially the electrical installations. That's to prevent failure due to poor contacts, shorts, okay, as well as examining pipes and steam jackets, right, for defects. So let's take a look at this camera. So here your IR, that's your infrared energy is going to come in, and here's hit the lens. You have a sensor, and then you have a processor, and then you have your memory, and then display. Okay. Alright, so that's it for the first part.